Solubility. Okay. Not everything dissolves completely, and that's what solubility is all about, just how much of this compound actually did dissolve. It could be a drug delivery system, just how much is it actually delivering into your blood. Or lava lamps are a good example of solubility. Those things definitely don't mix, otherwise it wouldn't be a lava lamp, right? But some of it actually does dissolve. I remember taking a biology class, and they put different drops on different areas of your tongue, and sure, you tasted it because the taste buds are everywhere. But these taste buds are distributed over your entire tongue, not just on certain locations. And it's a combination of those taste buds and the cells in your nose that actually give you taste. But here's a solid that I've had in water for about 15 months, I'd say. Does it look like it's dissolving? No, right? But a tiny, tiny amount did dissolve. So how do you calculate? And that's what makes today interesting. That's what makes life interesting, is that it's not, life is never that straightforward. A small amount did dissolve. How much did dissolve? You got to calculate it. It's important. It's important because that's what really all this stuff is based on. Not everything completely dissolves. So it might not be to this extreme where hardly anything dissolves, but the point is some of it does. And that's what we're trying to predict today. We're going to call it solubility problems, but we have a special equilibrium constant, Ksp. So Sp stands for solubility product, but solubility product. But just like any K with a subscript, you have to write the equilibrium a certain way. So we have to know how to write these Ksp reactions, just like we had to know how to write a Ka reaction or a Kb reaction. You have to know how to write a Ksp reaction. So we have this general solid, X2Y3 solid. Let's see if someone caught this from the reading. Vivian, how do you write a solubility reaction for a solid? Where does the solid go? Does it go on the reactant or the product side? Yeah, good guess. It goes on the reactant side. Okay. And then it has to go to its ions on the product side. What would the ions be, Crystal? What would the ions be?
What do you mean?
So remember how we did this? Like X is in these salts, these ionic compounds. X is always the cation or the anion? It's the cation, the positive one. The next one to the left of it is always the, sorry, to the right of it is the anion, negative, right? So we'll have X and Y. And you're right, X is positive something, Y is negative something. But what are those charges? The formula told you. X is a positive 3, and Y is a negative 2. Remember doing that? It comes right from these. Now, is it, we're not quite done, though. Is it balanced? So how do you make this balanced? 2 in front of the X and a, what do we call these again? Stoichiometric coefficients. Yep, stoichiometric coefficients. That's balanced. Okay. So we are already getting lazy because on these ions we should, I guess we're assuming water, we should write what subscripts? Subscript should we write if it's water? Aqueous, AQ if it's water, because it's dissolved. Another thing that we should really be doing is not this. All right? Draw a little extremely small one and a huge one going back, right? Because hardly anything dissolves in this. Yes, Crystal?
How come, you know how before in H2O we put liquid? Or did I just make that up?
No, H2O we put liquid.
So what's the difference whenever we put oxygen?
So the S is this. S means you got that crud on the bottom, the solid. So liquid means you have to have an L, right? So we're talking about solubility of a solid in a liquid. The liquid doesn't even show up here. And okay, let's try one of these. We have barium phosphate. How would you, Gabby, how would you write the Ksp reaction? The Ksp reaction for barium phosphate. Yeah. 3Ba plus 2. Perfect. Right? Does everybody agree? See how she did it? Okay. So this is how you have to write Ksp reactions. Otherwise, because these are all tabulated for different solids. So if you don't write the reaction the right way, you're not going to, it's not going to correlate. You're going to get the wrong answers. So you have to write the reaction the right way. Write the Ksp constant expression, Monica, for this reaction. So the expression, products over reactants, what would it be? Brackets plus 2. Good. Cubed. Keep going. Yeah. Ooh. Why is it 1? Because it's a solid, right? Okay. Products over reactants, the concentration, raised to their stoichiometric coefficients.
What about if we're putting solid on this side, what do we put on the other side for BA and B? We put opposite?
Yeah, again, see, we're getting lazy already. See how hard I'm forgetting, I'm not doing the double arrow. I'm not writing AQ on ions. So those are just things that we're going to assume, right? I mean, we should. We should be writing double arrows all the time, and we should be writing AQ on all ions. And you can go ahead and do that if you'd like. I'm just too dang lazy. Okay, I shouldn't be. Finding solubility. That's what today is all about. The homework is all about find the solubility of calcium phosphate. I don't know. Find the solubility of all these solids. When solving solubility problems, Danny, solubility is always the X in. The X in what? Does anybody know? Ice. It's going to be the X in ice. So what we're going to do is we're going to write the Ksp reaction and then do ice. Solve for X, that's your solubility. Like right here. Find the solubility of calcium fluoride in water. Okay. Well, also being a solubility is the X in ice, so we better make an ice table. We need a reaction, Erica, if we're going to do an ice table. What reaction should we write? Yeah, solid.
And then on the other side, minus. Positive.
First ion's always positive. Positive. Positive what? 2 plus F minus. Missing one thing. The stoichiometric coefficient of 2. Right? Okay. Now we're supposed to do ice. Okay. What did we do, Jasmine? How would you fill out this ice table? What do we do for solids and liquids in that ice table? We put dashes. Do we do it just in the initial row? Yeah, all the way down, so you don't screw up and put an X somewhere, because they don't show up. Solids and liquids don't show up in equilibrium constant expressions. They don't show up in Ksp expressions, any K expression. Tegan, how would you finish this ice table up?
With a dash for the initial.
Yeah, because they didn't say anything.
Positive X.
Positive X.
Positive.
Yeah, she caught it. 2X, okay. And then you add stuff up, X and nothing, and 2X and nothing. Okay. Jarixa, we're just going to find X and we're done. So what are you going to do now? We have to set up the what expression? Set up the Ksp expression. Because see how they told us what Ksp is? So 3.4 times 10 to the negative 11 would have to equal what over what, Jarixa? Products over reactants, which would be? Where does the 2 go?
On top.
With the fluoride, right? Okay, Jarixa set it all up for you. So if you can just put in the x's, Alyssa, what's this going to look like? What over what? We'll just put in for calcium. Calcium will be x. Close. 2x has to be squared because fluoride is 2x. Okay, so notice that's not 3x. That's going to be what on top? So just the 2x quantity squared alone is going to be 4x squared times x. 4x. Yeah. Okay. Now we're going to have to be taking some roots here to figure this out. If you want to solve for x, probably do what first, Danielle? If you want to solve for x. So 3.4 times 10 to the negative 11 equals 4x cubed. You hear what Tegan was mumbling about? Say it louder.
You divide Ksp by 4.
Divide it by 4.
Take the cube root.
Okay, so dividing by 4 is no big deal in the calculator. But how do you take cube root? Yeah, it's on there. But let's say it wasn't cube root. Let's say it was fifth root, right? Exactly. So I don't like using that cube root button because I like to do the same method for everything, right? Okay, let me show you how I do this. Right now we have 3.4 times 10 to the negative 11 equals 4x cubed. Well, let's divide by 4 first just to get rid of that. 3.4 times 10 to the 11 negative. Divide it by 4, about 8.5 times 10 to the negative 12. Okay, what I like using on this calculator is the x to the y button, because I can raise anything I want to any power. What's curious is, did you know if I take the square root of x, that's really x to the what power? X to the 1/2, right? So I really want to take this thing, this 8.5 to 10 to the negative 12, I really want to take the cube root of it. But that's really x to the 1/3. Okay, so all I'm going to do is I'm going to rate. So you can 8.5 to the negative 12 and push the cube root button to get your answer. Great. But I'm just saying, if there's a homework question that's not to the third, right? And if it's not cube root or if it's not square root, you're going to have to know how to do this. So what I'm going to do is raise this number to the 1/3 power. Now, I don't know what 1/3 is, but take 1 divided by 3, you get 0.33333 on the calculator. If you don't believe me, just try it. Take 1 divided by 3, you get 0.33333. So I want to raise this number to the 1/3, which is 0.33333. So take 8.5 to the negative 12, which is in the calculator, push the x to the y, raise it to the 0.33333. 2.04 times 10 negative 4. It'll work every time. If you want to raise it to the, you want to take the 5th root, well, let's write down our answer first. We don't screw this up. 2.04, make sure you can do this, 2.04 times 10 to the negative 4.
That's because like 3.46.
Okay. If it would have been,
Oh, okay, got it. Yeah. Okay. That's like
if it would have been 8.5 times 10 negative 12, just to play with this, equals x to the 5th. Okay? That means I have to take the 5th root, right? Or just do it this way. 8.5 times 10 negative 12, raise it to the 1/5. 1 divided by 5 is 0.2, so I'd put that number in the calculator, 8.5 10 negative 12, raise it to the 0.2, and I'd be done. Okay. But I think most of the time you're going to be covered with the cube root or the square root, so you're probably okay not knowing how to do this, but just in case. Okay, find the solubility. It's the X in ice. Here's our answer, except we don't have units. You got to have units or you're going to get knocked off here. Gabby, what units should we put on this? Molar. Exactly. Molar. Big M. Find the solubility in units of grams per liter. Well, we had 2.04 times 10 to the negative 4, right? Now, molar is what over what? Moles over liters. We want to get it into grams over liters. The liter part don't mess with. We have to go from moles to grams. Well, to go from moles to grams, what do you use? Mole bridge is this. This 2 moles of this for every 1 mole of that. That's mole bridge. So we're not using mole bridge. We're using molar mass. Okay. So the question is, molar mass of what? This is 2.04 to 10 negative 4 molar. That's what we said. But we didn't say molar of what? Of what? It's the CaF2. We should have wrote that in. And 1 mole of CaF2, I have so many grams of CaF2. So my answer will be grams of CaF2 per liter. So I just got to figure out what the molar mass is. What is it? Okay, around 78, Sabina says. So take that times 78, about 0.016 grams of calcium fluoride per liter. Okay. Make sense? Last question in here in this first example is find the solubility of calcium fluoride in 0.1 molar sodium fluoride. And they want the answer in grams per liter. So we'll have to do that last little step again. We're finding the solubility of calcium fluoride. We already did it. Can't we just write the answer of 0.016? What does this have to do with anything, the sodium fluoride? What changes? In initial. Oh, Sabina got it. Exactly. She said that the sodium's an alkali metal. It goes away. You're not even supposed to look at it. So that means you don't have pure water anymore. You're starting out with 0.1 molar fluoride. So you have something to put in the initial row, she says. She's exactly right. So it's going to be the exact same problem, but now you've got something to put in the initial row. So go ahead, try it. Set up your ice table, solve for x, and in fact, the math on this is going to be even a little bit easier because we get to drop the x. Solve, I'll go all the way to grams per liter. Now you have something to put in the initial row. In that initial row, by the way, there isn't any calcium. They didn't say that. Do we put 0.1 here, or do we put 0.2 there? Right? Because we have, it says 2Fs. I was trying to confuse you because a lot of people do this for some reason. Yeah, that'll be the change row, but this is 0.1 because they said it's 0.1 molar fluoride. So that's what you put there. You don't multiply it by 2 just because the stoichiometric coefficient is 2. Okay. But yeah, Crystal, you're right. This will be 2x, 0.1 plus 2x. And set up your Ksp expression. Products over reactants. Solve for your x. Get it into grams per liter. So can we drop the 2x? All right, what are you supposed to look at to see if you can drop the 2x? Yeah, definitely. Definitely can drop it. 10 to the negative 11? That's small. So you pretty much just have to divide 3.4 times 10 to the negative 11, divide it by 0.1 squared, and you'll get it. You'll get your x. Convert that into grams per liter. We'll have our final answer.
So we can drop all the x's if it's smaller?
Now, hang on. The only x grams of calcium chloride. Let's just get this guy done. What grams per liter? Okay, so the question is dropping these x's. Now the word that was kind of is not correct there, Crystal, is all of the x's. The only x's you can drop is when you're adding them to a number, because x has to be really, really small, because this is products over reactants, is KSP. and your products are all these x's. So whatever you get had better be 10 to the negative 11. So we know x is going to be extremely small, much, much smaller than 0.1. So all you can do is drop this part. If you multiply 0.1 times x, you get a really, really tiny number. So you can't drop that one. But if you take 0.1 plus 2 times a really tiny number, you still get 0.1. So this is the only one you can drop. So the only time you can drop these x's is when it's, you're adding it or subtracting it from a number. That's the only x's you can drop. (2.6 times 10 to the negative 7 or so. Okay. Now let's say you've got some time on the quiz to look at this stuff. All right. Here we got 0.016 is our original answer. Now we got 2.6 times 10 to the negative 7. The solubility went decreased or increased? All right, 0.016 to 10 to the negative 7. It definitely decreased. It dropped like a rock. And should it have? Whose principle was that? We have an initial fluoride. We have too much product. So the equilibrium shifts towards reactants. So solubility is going to decrease. Whose principle was that? Starts with an L. That guy. Le Chatelier or something like that. Okay? All right. Let's work on these. It's Friday and I don't feel like fighting you guys. Just leave you in your chairs. The solubility of magnesium oxalate in water is 0.0093 moles per liter. Find Ksp. So we need a plan. We could, I guess, is this a problem where we find x like this? No, it's not, because they already told us what x is, right? Isn't this our x? Is it in the right units even? Yeah, it's in moles per liter, so you don't have to change the units. They told us our x. So what? But you know that if you do set things up, you get your Ksp equal to some expression with x in it. So that's what I would do. I'd set up the whole ice table, just like this. I'd set up that whole ice table and write the expression, and then just solve for the Ksp. Right? So that's how I would handle it so I don't screw up. I would write the Ksp reaction, do ice, right? And then write the Ksp expression. It'll be Ksp equals some numbers with x in it. Okay? That makes sense? Did I lose you, Sabina? All right. Go ahead and write the Ksp reaction like we did here. Fill out the table, and then write the expression. And then substitute in the number for x, because you know what x is. And you'll get Ksp. Yeah, this is going to be an ion, and oxalate's an ion. And I don't know if you remember, but, well, magnesium is +2, so that means oxalate has to be a -2, because those subscripts are gone. Yeah, it has to be, because the solubility of this. So this has to be a solid, because the solubility is only for solids. I guess it could be a liquid too. Bless you.
Okay, sir.
Yeah.
How did you get that +2 -2?
Because I know magnesium
Is +2.
is +2. So that means oxalate has to be a -2, right? Because there's no subscripts down there. They're both 1s. So they had to cancel out on you. Mm-mm. Set up your ice table. What do we do under magnesium oxalate in our ice table? That's all dashes because it's a solid.
With 0.0093, would that be your final?
That's going to be your X. So set up your Ksp expression, and then substitute in 0.0093 for your X.
Oh, okay.
Right? Does this make sense? Dashes, X, 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 X. So pretty much all you have to do, right, is square 0.0093. You see that? Pretty much all you got to do is square 0.0093 and you'll have it.
Wait, I have to square that?
Because it's X times X is KSP. The solubility of silver bromate is 0.072 grams per liter. Calculate KSP. Very similar problem. You just have to do what first?
Figure out what you can.
No. It's a similar problem, but get it in moles per liter. Exactly. Convert this to moles per liter, and then do the same thing again. And then you'll do the exact same problem. So Alyssa, did you get the molar mass of that thing? 245? 246? 235. So several folks got 235 for the molar mass. All right? Several young ladies. I can't get that wrong in here. Notice how it's a 1-to-1 reaction again. The cation and anion are 1-to-1. So KSP is just going to be X squared again. All right?
Oh, it's just like
KSP will just be X squared again because it's 1-to-1. About 9.4 times 10 to negative 10. So if you got it, go on to the next question, 37. What is the solubility of lead fluoride in water? Now that's not 1-to-1, so I would actually write out the ice table.
That's not 4x with the
You'll end up with a 4x
to the third.
to the third. You'll end up with a 4x to the third. And they didn't care about units, so I guess they'll leave it in big M. Okay, we're almost out of time, but you may not have finished this question, but how does the ice table change for the second part?
Oh, you put that in the initial.
Put the 0.05 for the initial for lead. 'Cause I don't know if you remember your solubility rules very well, but nitrate is just like those alkali metals. You don't pay any attention to them. They're always spectator ions. Good, so that's the initial lead. Alrighty, so have a good weekend.